All right, let me do a very quick review of three-phase. Then I'm going to do a review of per unit and just key points, okay? And then symmetrical components. So this is a strategic review of the three-phase systems, key points that you need to understand, or think of them as potential landmines, okay? Pitfalls. ABC sequence versus ACB sequence, right? So in ABC sequence, you have phase A, phase B, and phase C. And ACB sequence, you have phase A, phase C, and phase B. It makes all the difference, okay? You do not have a voltage VBA in the positive sequence, and you do not have the voltage VAB in the negative sequence. And there are practical implications to this, okay? In terms of symmetrical components, balance systems, fault analysis, even in protection and control, if you get the sequence wrong, you can have nuisance tripping. So within the on-demand content, I have several detailed lecture slides. I'm going to briefly hit upon a couple of them over here as well. Please make sure that you have a solid understanding of positive and negative sequence. And from practical standpoint, as I mentioned earlier, I believe in Texas, we use ACB sequence. And in the Northeast, we use ABC sequence. And you can check out the grids and whatnot, utilities, and figure out where else positive is used and where else negative is used. So without any external adjustment, right, between the phase sequence, you cannot just directly hook up and connect the grids. Okay. Then the big topic within three-phase systems that you must understand is the working of a Y network, a delta network, and the delta Y transformation. As far as a Y network is concerned, if you look at the reference handbook, page 3.1.1, they have a very nice summary. They're telling you that the line voltage is greater than the phase voltage by square root 3, and the line current is equal to the phase current. That is true for the Y network. What they don't mention right up front over there is the relationship in terms of the phase angle. So the line voltage in a Y network leads the phase voltage by 30 degrees. As far as the delta network is concerned, the line current lags the phase current by 30 degrees. This is missing, but at least they tell you that the line current is greater than the phase current by square root 3, and the line voltage is equal to the phase voltage. I'm going to share those couple of slides, very interesting derivations that we did in the on-demand, just to remind you that you have the resources available to review whenever you want. And the delta Y transformation in FE electrical as well as in P power, I've reminded you guys multiple times that everything being equal, all else being equal, the best way to approach a three-phase system, three-phase calculations is by doing a YY. Okay, by keeping it YY. If you have a delta source, convert it into a Y. If you have a delta impedance, convert it into a Y. Because when you do YY, you're able to apply the Ohm's law directly and your calculations become so much easier. Unbalanced three-phase networks, we deal with them actually as symmetrical components. In the NCSP Power Reference Handbook, you're going to see a couple of problems where you have scenarios which are basically unbalanced, but on a line-to-line basis, you can still make use of the calculations and the equations properly, but you just need to be a little bit extra careful, okay? And three-phase power, all the equations are given, just be very careful. I recommend students to always start with the complex power, and as far as the line and the phase quantities are concerned, I recommend using the formulas involving the line voltage and the line current as compared to the phase quantities, because the line voltage and line current are independent of the configuration, and we can use the black box approach to then calculate everything else. Handling square root 3 and 30 degrees, that is super critical, and that brings us to the concept of the delta and the Y transformation, okay? So phase sequence, very quickly, this is what I was mentioning, and we've discussed this at length in the on-demand as well as live training. So phase A is being followed by B, is being followed by C, right? So you see the peak of A and then B and then C, and it keeps on repeating. So the voltages that we encounter over here, if we have VA, VB, VC very quickly again, you have VAB, you have VBC, and then you have VCA, which is VC minus VA. Okay, and this voltage corresponds to this voltage corresponds to this voltage corresponds to this. So please pay attention to how the problem is framed, right? Make sure that you are not interpreting a positive sequence network into a negative sequence and so on. And as far as the phasor diagram is concerned, the rotation is always counterclockwise, okay? You can be like, okay, Wasim, if I start rotating this clockwise, then A, if this is my reference, After A is rotated 120 degrees, I'm going to see a VC over here, right? No, the convention is counterclockwise rotation, and that's how you end up with ABC. And in this case, you have ACB. So you have A followed by C followed by B. And on the oscilloscope, if you hook this up, you're going to see A, C, and B. Okay. And then in this case, we're going to get these voltages A, C, B, A. So this becomes VAC, this becomes VCB, and this becomes VBA. In a negative sequence, you don't have anything called VAB. In a negative sequence, you don't have anything called VCA. In a negative sequence, you don't have anything called VBC. All right. Sometimes indirectly, if you're just given the line voltages, you can still figure out that what the sequence is. Okay. So that's a sequence discussion. And the big thing that we really need to understand are these derivations that we went through in a lot of detail, right? We went through the complex math, we extracted and dealt with square root 330 degrees, and I told you step by step how this all works out into giving us line current equal to the phase current, right? And the line voltage equal to square root 3 times the phase voltage. And we also commented and discussed how the line voltage in the Y network leads the phase voltage by 30 degrees and gives us these relationships. Okay, so very important. If you haven't already gone through this derivation, I strongly recommend that you go through it on your own in order to really get a good handle on square root 3 and 30 degrees. And similarly for the delta network, we have the line current lagging the phase current by square root by 30 degrees. You don't have to memorize it. We went through it step by step, use the phasor complex math, and the line voltage and the phase voltage are equal. So that's an easy relationship, right? But in delta network, it's really the angle where the action is happening, right? The magnitude, from a magnitude standpoint, the line current is square root 3 times the phase current, but it's really the phase angles that throw a lot of students off. Also because in the reference handbook, they don't explicitly mention it. Okay. And arguably the most important thing that you need to take away from the three-phase system discussion that we've had in the on-demand, the live training, and during the office hours is that try and always solve the three-phase system in a YY configuration. If you try anything else, you're asking for trouble. Okay. And this relationship, although not explicitly provided, you've derived it. You take the line voltage of a delta network divided by square root 3, pull the angle back by 30 degrees, and you have the equivalent phase to neutral or the phase voltage for a Y network. And when you have a YY network, life is so easy, right? It is so easy because on a per phase basis, you can apply the Ohm's law directly, and that would basically be it. Okay. Once you have one of the quantities, line quantities, then you can convert back into the delta, and then you can calculate the phase for the delta, phase current, line current, everything, the whole 9 yards. And if you want to learn more about preparation of FE Electrical and Computer exam and the P-Power exam, then check out these playlists over here. Thanks for watching, and I'll see you soon in the next video.